So we have seen that how we can define a mathematical definition of a grammar. Now we will proceed with some uh, terminologies that will be required frequently throughout this subject. We will realize it very soon, and maybe we will be habituated with this terminology. I mean, day by day. So we will start with the very basic, the first terminology, that is what we call symbol, which is basically a basic building block of any language. For example, if I ask you about binary language, and if I ask you what should be the symbols present in a binary language, you will be it's 0 and 1, that's all, because it is binary. If I ask you about the basic symbols present in English language, you will say that it is small a to small c, capital A to capital, sorry, small a to small z, capital A to capital Z, and all. Like this depends upon the language that we are trying to generate. We first have to identify what symbol we should present in the language, because that's totally depends upon the designer. Suddenly one day, if you think that you want to design a new language, the first thing that you have to note it, that what are the symbols you will allow in your language, because binary language will not allow ABCD. English language will not allow 0 1. In the same way, you have to also define that which symbols you have to allow in your language. The next one is what we call alphabet. What is this? This is a set of symbol which mathematically we represent by sigma. This particular symbol, and this symbol will be frequently used throughout this subject, so you must be habituated with this symbol for future use, for near future. So that means each and every language must be associated with some alphabet, and alphabet will contain those actually set of symbols. The symbols actually a single character, plus minus a b c d 0 1, that's all. And alphabet say that set of all these symbols. That means alphabet of English language will contain A to Z. Alphabet of binary language will contain 0 1, as I have shown over here. That's all. Now next one is that what we call string. What is string? A sequence of symbol of an alphabet. Sequence of a symbol mean if I consider uh, English language, I know that the alphabet of English language is A to Z. Now a string can be A B C D, a string can be A B C D A B A string can be all A's or all B's or all C's, something like that. It can be anything. We are not considering the length of the string. We will see it very soon. But it can be of combination of any symbols. But that does not mean that that string is the correct string of this particular language. We have not yet defined that. We are saying that combination of any symbol, a sequence of set of symbol can be a string. Now whether it is a valid string of that particular language, to do this we have to define this language, which says a collection of string. For example, in English language, hello, how, you, and this type of lot of different words are correct word in the English language. So if I say that good morning to all of you, it is a correct string of English language because this string is present in this particular set. But if I say that hello ABCD, it doesn't make any sense. It is not a part of this English language, you can say. So that means for any case, for any language, not only for English, even for uh, C language, for example, if I define a C language, for example, with 0, 0, 1, 1, 0, it's not making any sense of C language. So that means we have to realize this particular set at the time of starting creating this language actually. So now question is that so this is all about this four important terminology we have, and which these four terminologies will be used frequently, very frequently throughout the subject in future. But still I want to extend it more because we have not yet defined about the length of the string. We are saying that it's some collection of string. Language is a collection of string and string is a sequence of symbol. But what is the length? We can define this language with respect to length of the string also. For example, if I extend it more, suppose that we have a we are planning to create a language whose alphabet is A, comma B. That's all. Okay. So that means C is not allowed, D is not allowed, anything is not allowed other than A and B. And here I can say that suppose I am planning to design a language L1 which says that language of all string of length 1. And how we can define it mathematically? We can define in this way. We can define in this way. L1 equal to, within bracket A comma B means is the alphabet, which is alphabet superscript 1. And why only A comma B? Because since the length is only 1, either A will be there or B, that's why. But if I extend it more, a language of all string of length 2, since I have a symbol A and B, we have not said that how many sequence. We have not said that repetition is not allowed. It can be any sequence, just like I told you that all A's or all B or all C can be a string also. That means that is why if we consider this language L2, which is string length of string of length 2, here I can say that A, B is possible. Similarly, A then B and B then is possible. But other than these four different cases, you will not find out any fifth situation, fifth string which will be within this language. And this one we can, as a shortcut, we can define as sigma superscript 2. Similarly, if you consider language of all strings of length starts with A, suppose start with A, and I have not yet defined, suppose this is the L3, so start with A. Start with A means, you see, I have not here defined the length. You see, this is another type of language where length is not defined. But I have said that the language has to start with A. That means if you consider at least these four cases, this AA is a correct string under this language L3. It can be a element of this set. L3. BB cannot be element of the set because this particular string starts with B, not A. Similarly for this one also. But AB can also be an element of this language L3. And you see, since I have not defined the length, that is why I can have infinite number of cases possible where the string starts with A, because after A, since there is no restriction of length, I can have many options possible, like after A then B, or maybe AB or BA or BB or AA or all A, like this it will continue. We will not, it's not possible to end. Still one interesting language is left, that is what we call L0. I can say in this way, that which is language of all string of length 0. So naturally the question will come that if the string has length 0, then how I can define it? That is actually what we call empty string. This is what we call this is what we call sorry uh, empty string. Or I mean, I must I'm sorry, it should be empty string. Obviously empty string because there is no string. It should be said as empty language. So this empty language is going to be very vital in future. We will see it very soon. Now question is that why we are actually, thinking about all different type of languages and all. By the way, to understand, before we understand that, let's extend it little bit about the language that we have seen sigma 1, sigma 2, sigma 3, sigma 0. There is a mother language which is all above all these languages, what we call this sigma star, which is also said as clean closure of sigma, which says that a logically logical OR of all the above languages possible, like sigma 0 or sigma 1 or sigma 2. So many different type of cases possible. And if you just write this, it will be something like this, which will never end. So this star means any combination including empty strings. Now if I want to exclude this empty string, it will be basically what we call sigma plus. You see, sigma plus. This is also any combination. There is no doubt, but only difference is that the plus mean any combination excluding empty string. And that's why you see the sigma 0 that is present over here, which is absent. We started from sigma 1. We have not included this epsilon over here. So this, I mean, this type of these symbols, that sigma star, sigma plus, and all that we have seen will be frequently used in near future. That's why you must be habituated with this. That's why, well, I mean, I have discussed about all this one, but ultimately still one thing is not clear, that why we are thinking about all this. So let's try to analyze it. That this analysis will actually help you to realize what is the exact practical application of the automata theory and why this subject is so important for us. So before we dive into this the application of automata, to realize the application of the automata theory, one question I have, that the program that we write, we are all habituated with writing C program or Java program or C++ program. What we do, we write a program in some editor and we have some compiler in our hand. What we do, we just run our program in some particular compiler, and the compiler actually find whether the string is, whether there is any syntactical error or not. If there is a syntactical error, then it actually just highlight that, or if it doesn't have any syntactical error, then it basically tell you, it basically execute, right? But one thing we basically overlook is that how this program is input to the compiler. Always remember one thing, before explaining this one, let me tell you one thing. I have not included any pre-processing part over here, just to avoid the complexity to realize exact scenario. Okay, always remember, we know that if we write some pre-processing part, for example hash include stdio.h or cona.h or something like that, or hash define, we know that this pre-processing part actually executes before the program go into within the compiler, and whatever statement that we have in the header files that are actually added above this program, that we know, right? But anyway, if we don't have, then that will be not be added. So just for timing, you forget about that, there is no pre-processing part. Okay, now if this program should be input to the compiler, how it gives how it goes as an input. Always remember one thing, compiler doesn't accept the program in the same way as you have written. The first job of the compiler is to make this particular program of number of lines into a single length string. A single line string. What I mean to say, that whatever you have written in this way, it will first convert in this particular form. So that means technically, if you write your whole program in only one line in this way, you are not wrong. You can try it in your home with any editor. If you just write this program only in one line, as I have written over here, and if you just run this program in the editor under the compiler, you will see that your program will correctly execute. The reason is that how many lines you have written you have written in the program in some editor, it is not important for the compiler, because compiler convert your program of say n number of line to a string of only one line, and this string actually goes as an input to the compiler. And ultimately, what is the first job of the compiler? If I ask you what is the job of the compiler, if you say that it runs the program, it is no, you are not fully correct. The first job of the compiler is to realize that whether the program you have written is syntactically correct or not. If it is syntactically wrong, then it throws the error. If it is syntactically correct, then it actually proceed with the other steps that is defined within the compiler. Now, what is a compiler? Compiler is basically, you can assume, as a machine which takes an input and produce some output, right? So my question is that if I ask you about some English sentence and I ask you whether this is correct or not, you will say yes, this is grammatically correct or this is grammatically wrong, because the grammar is in your mind. Now question is that how compiler realize this one? Because compiler is a deterministic machine. If this deterministic machine want to realize that this some, I mean, to realize whether a particular string, or basically string, right? Because ultimately the program that we are considering over here is basically the string. This is the basically string is nothing but the program. So if a compiler want to realize whether the program or the string is a proper string within the language, specific language, then it has to follow some deterministic steps or rules. Now, how it is possible? What is the base? I mean, trivial approach. The trivial approach can be. So this is a very, I mean, most important part of realizing the purpose of automata theory. So please watch it very carefully. So that means, you see, just assume that we are considering C language. That means I can say the collection of, I mean, we are considering that we have a the alphabet of the C language is say sigma C. Okay, representing, it's just a representation. Sigma C is the alphabet of the C language. So what we have in the sigma C? Sigma C contain this small a to small z, capital A to capital Z, 0 to 9, all the mathematical and logical operations, and many more. As we use writing program, we frequently use all these symbols when write a C program. So these are nothing but, as a set, will basically represent sigma C. Fine. Now what is the trivial approach? That there is, suppose, I mean, I have n number of programs. Okay, I have n number of programs which is stored in some computer memory. So what a compiler can do? Compiler can accept this set of programs from the computer memory. At the same time, compiler also accept an input program, something like what we have seen in the previous one, this one. So this is the input program the compiler has to realize, and that is represented over here, this one. At the same time, compiler, what is the purpose of the compiler? Let's try to recap again. That purpose of the compiler is to realize that whether this program is correct or not, as simple as that. So to realize this, what is the base trivial approach? That I have stored all the possible programs, the valid C programs, in a computer memory, and I'm checking the actually the compiler. Compiler will check this program with all these programs sequentially. A very simple linear search, for example, that whether the program exists in the set or not. Something like, what is the program? Program is the string, and these are those correct set of string, because valid programs, that mean correct set of string. So these are all correct string present in the C language, possible, all the correct string. So if it's just consider that a string matching problem, that compiler is trying to match the string present as an input over here with the all the correct strings that represents the computer language as a whole. But is it really a solution? It is not a feasible solution. Why? The reason is that computer language doesn't define any length of the program. It means that a program of length 10 is correct, 10 lines. A program of 100 lines is correct. A program of 10,000 or 1 lakh line is also correct. May be correct grammatically. So if there is no restriction about the length of the string, then what we have seen? We have seen that the number of string can become infinite. Just we have seen in the previous case over here. You see over here, this one. I have not defined any length, and that's why it cannot say that where it ends. So the same situation arises over here. So that means basically the P1, P2, P3, Pn that I've shown over here, the value of n is infinite. That means you have an infinite number of program, and if you still for the sake of just time, if I consider I want to store that infinite number of program, still I will not able to store. Why? The reason is that computer memory is a finite. You cannot store an infinite amount of data in a finite memory. That is why this solution is totally wrong. It's not possible. That means I have to find some another way by which the compiler actually can do the same task. And to find the solution of this situation, the automata theory came. How? You see, the same situation arises over here as shown over here. Instead of, since it is infinite, that's why now what I will suggest, that instead of considering infinite number of programs, let's try to realize with the respect of the grammar of the C language. Because in case of a grammar, what we have seen, a grammar is defined by 4 entities: V, T, P and S. V is finite set of non-terminal, T is finite set of terminal, P is finite set of production rule, and S is the start symbol. Everything is finite. That you can store within the computer memory, and which itself represent the whole language, the rule. So instead of just considering whether a program is correct or not by a string matching scenario, I can consider something like whether this particular string is following the rules of the C language grammar or not. I can check in this way. And in this particular approach, this particular storing the grammar of a C language in a computer is possible, because it is everything about finite over here. And now, so that means the idea is that somehow you have to find out whether this particular program is basically following the set of grammar, this particular program is following the grammar of C language or not. In a just different way, you can consider the similar situation. You can consider the same situation actually. Consider as whether, you can say that whether this grammar can derive the string that represents this program. Just like I have defining with the product, using the production rules in some particular order, we have derived the sentence the boy eat an apple. In the same way, obviously, if the program or the string is correct, that means using the production rule of the C language grammar in some particular order, the compiler must be able to derive the string. And if it is possible, then that means the program is correct. That's why it is possible. For example, instead of writing the boy eat an apple, if I say that I have a sentence the boy eat the apple, or maybe the boy eat is apple, I know that the sentence is wrong, but if I say for a time being that there is a sentence the boy eat is apple, is it possible to derive this sentence with the set of production rule? It is not, because any order of the production rule that is defining that language for that time being will not be able to derive that sentence. That's why. In a similar way, if there is something missing in the program, that means in the string present here will be wrong if it has some, if there is anything missing, then with some combination of the production rule of the C language, it will be not possible to derive that particular string. So the compiler will check this one, that whether its derivation is possible or not. If it's possible, then there is no syntax error. If it is not possible, then there is a syntax error. So that means we can assume the whole situation as a set membership for a language L. Is that given a string X, we have to decide whether the X under this language or not. So since why we are considering set membership problem? Because language is a set. We have seen that language is a set of valid string. So from this point, very interesting theory came, not theory actually, very interesting classification of grammar came with the help of a very well-known scientist, what we call, whose name is Abraham Noam Chomsky, who born on December 7, 1928. And we say he was a linguist, some philosopher, but cognitive scientist, but he was no more associated with computer science at that moment. But still, he has an enormous contribution in the field of theoretical computer science, and because of him, all the languages that we actually deal with today has been designed. Without this philosophy about the classification of the grammar or the mathematical definition of this grammar, it was not possible to derive any language of like C, Java, and many more. Anyway, so let's dive into this classification of the grammar. We have actually 4 different types of grammar possible. We have defined that a grammar can be combination of V, T, P, and S, and among them P represents the production rule. If you closely try to realize that what are the basic difference between those 4 types of grammar, you will see that the difference is actually with respect to the type of the production rule. Type of the production rule in the sense, so let's start from the beginning. You see the serial number 1 I've given as type 3, and it is not wrong, it is correct. The first one we call type 3 grammar. Okay. Also we call regular grammar, whose type of production rule is something like, you can see A, for A can be rewritten as capital A can be rewritten as capital A followed by small b, or capital A can be rewritten as small b. And what it signify? It signify that, always remember one thing, we represent non-terminal as capital word with capital letter, and terminal as small letter in automata theory. So that means we can say that capital, a non-terminal can be rewritten as a non-terminal followed by a terminal, a single non-terminal followed by a terminal, and also I can say a non-terminal can be represented as or rewritten as only a single terminal. Even I have written here also that A belongs to this set of V. V is the terminal set of non-terminals, and T is the set of non-terminals, this one. So B belongs to this T. But there is one more situation possible, that you can something like, let's write it, let's write in a, say, another color, for example this one. You can also say that A can be rewritten as B followed by capital A. Okay, this is also correct. But remember one thing, you must have only one terminal, one non-terminal in the right hand side or in the left hand side. So this is also possible. Okay, this is also possible. So ultimately, one thing is sure, that in the left hand side of this arrow symbol, in the LHS, we will have only one non-terminal. In the right hand side, we will have only one non-terminal followed by a terminal, or a terminal followed by a non-terminal. Anything is possible. And also it is possible that only one non-terminal or only one terminal. That means you can say that if I ask you that whether this is correct or not, say A, B, is it a valid production rule of regular language? No, it is not. Why? Because I have two non-terminal side by side in a production rule, which is not possible. I can have only one non-terminal in the RHS, which may be followed by some terminals. Okay. And now naturally, okay, let's proceed with the other languages. The second one, the type 2, if you consider, we call context free language. And what does it mean? We will realize it soon. So the type of production rule of the context free language is something like what is written as can be rewritten as alpha, where A belongs to non-terminal and alpha belongs to V union T whole star. What does it mean? Union means or. And what does star mean? We have seen that star mean any combination. So we can say this particular V union T whole star signify any combination of terminal and non-terminal. That means this particular string, this particular production rule, which was not true, which was not correct under regular language concept, but it is correct with respect to context free grammar. I'm sorry, which is not true for regular grammar, but it is true for a context free grammar, because alpha says that any combination, and under any combination it is possible to have more than one non-terminal in the RHS, even there is no terminal. So that means, for example, you can say that A to AB, it is also correct because it is also some combination of terminal and non-terminal, right? I know that A to capital A small b is correct in regular grammar, but it is also correct in context free grammar also. Similarly, like A2, capital A, capital B, small c. This is also correct in case of context free because it is some combination of terminal and non-terminal, which is basically not true in case of regular grammar. For example, if I say only A2, a, small b, small c, this is also correct with respect to context free grammar. So that means any combination is possible. Like even A2, a, small b, capital C, capital D, this is also correct. So because any combination. So what difference we can find out in these two cases? We have found a very a huge difference with respect to the RHS part. You see, if you check the LHS part, they are same. Because in the LHS part, for regular grammar, we have only one non-terminal in both cases. And in case of context free grammar also, we have only one non-terminal. But in the RHS, we have much more restriction in case of regular grammar, which is loosened down little bit in case of context free, right? So now let's go to the context sensitive grammar, and the type of the production rule is defined something like this, that alpha a beta can be rewritten as alpha gamma beta, such that alpha and beta, this two part, is basically some combination of terminals. Okay, this A has to be some non-terminal, and gamma is written as T plus. You see, this is very important. T star, V and T plus. What does it mean? What does T star mean? Any combination. Not only any combination, but also empty. So that means I can consider a situation that alpha and beta is basically an empty. Right? So if alpha and beta is basically empty, that means just assume that they vanishes. You have only one A in the left hand side. It is possible. And in the right hand side, since alpha beta vanishes, then alpha beta also vanishes in the right hand side, because this is also alpha beta. But in case of gamma, it is said that T plus, that means there will be at least one terminal in the right hand side. At least one terminal. That means here, in other words, we can say that in the context of alpha and beta, A can be rewritten as gamma. That is why the name came context sensitive grammar. And you see, one more, a very important difference from here we can find with respect to the previous two cases is that in the LHS of this production rule, there is a possibility to have some combination of terminal and non-terminal. But what is the restriction? Restriction is that there will be exactly one non-terminal in the LHS. But that does not mean there will be no terminal, right? Like in the previous two cases, it was there will be exactly one terminal. There is exactly one non-terminal and I'm sorry. Okay, sorry. In the previous two cases, it was there will be exactly one non-terminal and no terminal will be there, right? But in the third case, what we have seen, that there will be exactly one non-terminal, but other than this non-terminal, I may have some terminal also, which is represented by this alpha and beta, and which may not be possible also there. That's why I have written as here it is considered as T star. That means since star is there, that means any combination including null. And since plus is here, that means any combination including at least one terminal. And here is the difference. So that means just like in the LHS there was only one terminal, here LHS is loosened down. So in the previous two cases, at least, we had a restriction about the length of the LHS. But now in the third case we can see that this restriction is loosened down. I can have more than one characters in the LHS, and that can be written as with respect to this following rule. And if you go beyond this context sensitive, by the way, this context sensitive grammar is also called length increasing grammar. And if you go down again, I mean for the type 0, we say it is unrestricted grammar, which say that it is basically, you can say as U can be rewritten as V, where both U and V can be any combination of terminal and non-terminal. Now see, here if you just try to relate the restriction with respect to the previous grammar, here we had any combination of terminal non-terminal, but one restriction was that only one terminal will be there because it is V, not V star or V plus. That means only one terminal will be there, only one non-terminal will be there, and after that, before or after that, maybe there will be some terminals. Here this restriction is still loosened down in the left hand side because U will belongs to V union T whole star. That means any combination of terminal and non-terminal. Also in the right hand side. So if you closely try to realize, try to make a comparison between these four different types of grammar, what you will see? You will see that this regular grammar is actually what we call most restricted grammar, right? Most restricted. And this restriction is loosened down in context free. It is much more loosened down in context sensitive. And it is totally loosened down in case of unrestricted grammar. That's why the name here, unrestricted. So these different type of grammar actually will generate different type of language. And one thing is very important over here, that this context free grammar is going to be very vital in future. The reason is that all the natural languages that we have, like Bengali, English, Hindi, whatever you can say, all these natural languages are context free language. So context free language means the grammar behind these languages are context free. So the grammar of English language is a context free grammar. The grammar of Bengali language is a context free grammar. Grammar of Hindi, Urdu, Nepali, whatever you can say, are context free grammar. That's why this particular grammar is going to be very vital in future, and corresponding language that is generated by this grammar is going to be vital also. So we will see very soon that how this different type of grammar generates different type of languages. But one thing still is left, that is ultimately we can see that this grammar is basically generating the language. So what I can say, that we have a language in one side, so that means if I can assume like uh, I can assume like that we have a language here, some language which is basically generated by some grammar, right? But question is that this language has to accept by by something also. I mean that suppose that suddenly tomorrow you realize that you want to generate your own language. So what you will do, you will start noting down your alphabets and all. You will create your own set of production rules for generating various sentence or string of your language. But if there is nobody to receive your sentence, then there is not making it's not making any sense to generating this language, right? You want to talk with some people with that new language, so that people has to realize that whether what you are saying and whether the whether the sentence that you are or string that you are using in that modified language is correct or not, something like that, right? So that means the similar situation, if you want to just realize with respect to computer science, that if I define a new language, say C triple plus, like we have C double C plus plus, and now suddenly next day if you feel that you want to design a new language C triple plus, then you will define the grammar, you will define everything, but there is no compiler to accept your language, so it will totally fail. That means you have to define some machine in the sense a deterministic machine or an algorithm or something like that, who will basically accept your language. So somebody should accept your language. This is done by different type of machine, or in other words algorithm. Some algorithm, some program, and this machine will depend, the type of machine will depend upon the type of grammar that you are using in your modified language. If you define your modified language as a with regular grammar, then the corresponding machine that you will require will be finite automata, that we have seen over here, this one, finite automata. If you think that you are trying to you are if you are planning to design a modified language which is following context free grammar, then the corresponding machine that you have to design to accept that, in case of computer science I'm saying, will be what we call push down automata. If it is context sensitive grammar, it will be linear bounded automata. If it is unrestricted grammar, this is, it should not be unrestricted machine. Here it should say it should be Turing machine. Okay, or some people say Turing machine. So this Turing machine will accept the grammar of understood language. Now, very frequently we are using this word automata as a, you must know this, you must know that this term automata is actually it's actually derived from a Greek word which it's not possible to pronounce because we don't know Greek letters properly, but which means that it's something which is self-acting. Okay, and one thing, automata is a plural term. The singular term of this machine what is called automaton. Okay. um, Anyway, so we use frequently automata or automaton, interchangeably throughout the course. So there is no difference we generally consider about these two words. Anyway, but ultimately the automata or automaton, this particular mean is an abstract self-propelled computing device. That means it actually automatically uh, uh, something like there is, I mean, you can consider as something like uh, it has some intelligence within the machine that follows some predetermined sequence of operations which done automatically. But remember one thing, automata is know-how related with this word automatically. If someone asks you that how this automata word came, you don't say that since there is a machine which accept the language, accept the string of a language automatically, that's why the name is automata. It's, there is no difference, I mean there is no relation between these two words. Okay, so anyway, so you must understand, you must, I mean remember this particular terminology. So what we have seen, at least the basic idea we have seen with respect to these four different cases. If we have seen with respect to the restriction, if I ask you that you basically make a relationship between these four different types of grammar, how you can, I mean express this? We can express this with respect to a Venn diagram. A Venn diagram looks something like this, where the inner circle, most inner circle is the regular grammar. It's very trivial, right? Because we have seen that it is most restricted, that all grammar are not regular. I'm sorry, the grammar which are not regular may be context free. I mean, in an inverse way, you can say that every grammar that is a context free grammar is also a regular grammar, because you can say that I'm sorry, I had a mistake. Every grammar which is a regular grammar is also context free grammar. For example, a small, capital A to capital A small b. This is the correct regular grammar, and this is context free grammar. Okay, this is correct for regular grammar, and this is correct for context free also. Capital A to small b, this is correct for regular, this is correct for context free also. Capital A to small a capital B, I mean small b capital A, correct, because any combination in case of context free we have seen. Now A to A B, it is wrong, it is not possible in case of regular grammar, but it is correct in case of context free. For example, something like B B A B A B C, this is wrong, but this is correct in case of context free. So at least in this way, I have many more examples you can give. But one thing we can see, that up to this one, if we check, that I can say that those grammar which are regular, those are also context free. But if a grammar is context free grammar, it does not mean that the grammar will be regular also, because of this loosen down of restriction in case of context free. Similarly, we have seen that in case of context sensitive, it is also much more loosened down. So that means all the grammar which is context sensitive may not be regular, but all the context free grammar is context sensitive. And similar situation for unrestricted also. So if, and this particular Venn diagram conceptually is very vital to realize what is the exact relation between these different types of grammar. So we will study these four different types of grammar and corresponding four different types of machine throughout this particular course of automata theory and uh, and formal languages. Okay, so we can stop class over here for today. I mean, next day we will start from one of these four grammars, and we will start from this regular concept of regular grammar, and then we will proceed accordingly. Thank you.